Hi, I'm Osama Ansari, a PhD candidate at the University of Saskatchewan, Canada. In this presentation, I'll present our recent work on short-term reliability evaluation of generating systems using fixed effort generalized splitting. Short-term reliability measures the ability of a power system to withstand unexpected disturbances, which originates from component outages and variation in generation and load profiles within a short span of time in the future, also known as the lead time. The development of short-term reliability evaluation techniques could lead to replacement of existing deterministic techniques such as N-1 contingency analysis with fully probabilistic approaches. Now, mathematically, the short-term reliability or risk index can be represented by the expectation of a performance function, h of x. For generating systems, h of x is defined as an identity function of s of x less than or equal to L, where S of x represents the total available generation capacity and L represents the expected load during the lead time. F of x is the probability distribution function, or PDF, representing the uncertainties of a power system. The techniques to evaluate this expectation can be classified into two main categories: analytical methods and simulation techniques. Analytical methods, such as state enumeration, can calculate the exact reliability indices. However, they are computationally intensive for practical sized systems. In simulation techniques, Monte Carlo simulation can be used, which is robust to system size and can also consider complex operating strategies. But it is also computationally inefficient for evaluating small probabilities or rare events. In recent years, importance sampling has been adopted for reliability evaluation. Although importance sampling is computationally efficient, it has certain limitations. It is difficult to obtain importance sampling densities for non-exponential family PDFs, and it suffers from degeneracy for high-dimensional cases, which leads to variance explosion. In this work, for the first time, importance splitting is proposed to be adopted for short-term reliability evaluation of generating systems. The basic idea behind importance splitting is to employ sequential sampling to probe regions of sample space which are of interest for rare event simulation. Starting from the initial point, multiple trajectories are generated. Then those trajectories which down crosses an intermediate level, let's say L1, are selected. From these trajectories, further multiple trajectories are simulated and the process is repeated until there are enough trajectories or samples in the region below the load during the lead time. In this way, a large number of samples are generated where the load curtailment occurs. The conditional probabilities are then calculated using the following equation, where n sub t represents the number of samples that enter into the region below level L sub t, and s sub t represents the number of new trajectories generated from each of such samples. Traditional importance splitting methods are generally applicable in dynamic Markovian setting. The expectation in the previous slide represents a static non-Markovian case. Therefore, in order to use importance splitting for short-term reliability evaluation, we propose to adopt fixed effort generalized splitting. In this method, Markov chains are generated from each sample that downcrosses a certain level. These Markov chains have a kernel density function given by s sub t of x. We proposed a component-wise Metropolis-Hastings Monte Carlo method to generate such Markov chains in this paper. The details of this algorithm, as well as the complete description of the fixed effort generalized splitting method for short-term reliability of generating systems are provided in the paper. In order to investigate the performance of the proposed approach, case studies are performed on a 24-bus IEEE reliability test system. The lead time is set to 2 hours, and the table below shows the risk indices and the number of Monte Carlo samples required for both crude Monte Carlo simulation and the proposed fixed effort generalized splitting based Monte Carlo simulation. As it can be seen from the table, the proposed approach outperforms the crude Monte Carlo simulation in terms of computational burden. Moreover, as the risk index decreases, which means that the rare event becomes further rarer, crude Monte Carlo simulation techniques become computationally prohibitive, and for some cases do not converge within the given computational budget. On the other hand, the proposed method does not suffer from a large increase in computational burden, even at lower values of risk indices. From the results, it can also be noted that when the risk indices are higher, the proposed approach does not significantly improve the computational performance over crude Monte Carlo simulation. However, it should be noted here that for operational reliability purposes, the short-term risk indices are usually very low. The difference between the risk indices in the two methods are also within the acceptable coefficient of variation, which is set to 10% in this paper. We also investigated the impact of load uncertainty, where the load forecast error is modeled as a simple Gaussian distribution. As expected, the results indicate that the increase in uncertainty corresponds to lower short-term reliability or higher risk indices. Compared to previous case studies, the increase in computational burden is also evident due to the inclusion of load uncertainties. The impact of wind generation is also studied, where wind forecast error is modeled as a Gaussian distribution similar to load forecast error. It should be worth noting here that the proposed approach is very versatile and does not restrict any form or shape of PDF for load forecast error as well as for wind generation forecast error. In fact, any forms of PDF, whether parametric or non-parametric PDFs, can be used as long as samples can be generated from those PDFs. In case A, a 155 megawatt conventional generator is replaced by a wind farm. In case B, only conventional generators are considered in the original 24-bus IEEE reliability test system. The results indicate that when wind generation with a forecast value of 155 megawatt is committed, the short-term reliability drops, although the maximum available capacities of the system are identical in the two cases. At higher wind generation forecast values, the short-term reliability expectedly improves. These results indicate the limitation of deterministic methods which do not respond to the uncertainties in the power system. So in conclusion, fixed effort generalized splitting, which is a variant of importance splitting method, here is adopted for short-term reliability evaluation of generating systems. The proposed approach is versatile and allows any form of PDFs to be integrated in the reliability evaluation process. Results show that the proposed approach outperforms crude Monte Carlo simulation in terms of computation. For large risk indices, the increase in computational performance may not be as high as for lower risk indices. Further work is required in order to analyze the variance of fixed effort generalized splitting estimator and also investigate other variants of importance splitting, such as fixed number of simulations importance splitting. Thank you for listening to this presentation. I'll be happy to answer any questions through this platform. Or if you have any further questions, feel free to email me at oa.ansari@usas.ca.